The MD-11 is designed to fly on two engines. That's the entire point of redundancy. On November 4th, 2025, UPS Flight 2976 lost its left engine during takeoff rotation. A fully loaded MD-11 should have been able to climb away. It didn't. It barely reached 30 feet before crashing into buildings beyond the runway. The NTSB's flight data recorder shows something that hasn't been widely discussed. Engine 2, the tail-mounted engine, experienced what investigators call minor perturbations in its parameters moments after Engine 1 separated. Video shows flames erupting from the tail. If debris from the left engine was ingested into the center engine, the crew didn't lose one engine, they lost two. Let's establish what we know. UPS Flight 2976 and MD-11, F freighter registration N259UP. Departed runway 17R at Louisville Muhammad Ali International Airport at approximately 5:13 p.m. Eastern Time. The aircraft was bound for Honolulu, Hawaii, an 8.5-hour trans-Pacific flight. It was loaded with up to 20,000 packages and carried approximately 34,000 gallons of jet fuel for the journey. 3 experienced crew members were aboard: Captain Richard Wartenberg, First Officer Lee Truitt, who was the pilot flying, and Relief Officer Dana Diamond. Between them, they had over 33,000 hours of flight experience, including nearly 15,000 hours in the MD-11 specifically. Weather was not a factor. Clear skies, 6-knot winds from the southeast, 10 miles visibility. This was a routine departure in ideal conditions. The takeoff roll proceeded normally. The FDR shows all 3 engines operating at takeoff thrust, parameters within normal limits. At approximately 17:13:11, the aircraft rotated. Rotation is the moment the pilot pulls back on the yoke and the nose wheel lifts off the runway. It's also the moment of maximum stress on the engine pylons, with the full weight of the aircraft transitioning from ground to airborne. Within seconds of rotation, the left engine and pylons separated from the wing. Airport surveillance cameras captured the sequence. The pylon's aft mount failed, the engine pitched forward around its remaining front attachment. Then, the front mount gave way. The engine and pylon assembly, still producing thrust, tumbled upward and backward over the wing's leading edge before crashing onto the grass beside the runway. Fire erupted at the separation point on the wing and on the engine itself. The aircraft was now asymmetric. 1 engine gone from the left wing, with 2 remaining, engine 3 on the right wing, and engine 2 in the tail. Standard procedure is clear. After V1, you don't try to stop. You fly the aircraft, deal with the emergency airborne, and return to land. The MD-11 should climb on 2 engines. That's what the certification standards require. But Flight 2976 didn't climb. It reached approximately 30 feet above ground level and never got higher. The crew cleared the blast fence at runway's end, barely, before the left main landing gear struck the roof of a UPS warehouse. The aircraft continued another 3,000 feet before crashing into a petroleum recycling facility and scrapyard, killing all 3 crew members and 12 people on the ground. The question that has haunted this investigation: why couldn't they climb? One video taken from behind the aircraft shows something critical. As the MD-11 struggles just above the ground, flames can be seen erupting from the tail-mounted engine 2. Not a continuous fire, but distinct puffs of flame, the signature pattern of a compressor stall. Captain Brian Scheibner, analyzing the footage, identified what he believes happened. Debris from Engine 1 was ingested by Engine 2. Think about the geometry. Engine 1 separated during rotation and tumbled over the wing. As it came apart, high-velocity fragments, fan blades, compressor components, fuel were thrown in all directions. The tail engine sits exposed at the base of the vertical stabilizer, its inlet facing directly into the slipstream. Any debris carried over the aircraft would have a direct path into that engine. A compressor stall occurs when airflow through the engine becomes disrupted. The compressor blades are designed to move air smoothly through a series of stages, each increasing pressure. When foreign object debris enters the inlet, it disrupts that airflow. The compressor can't maintain proper compression. The result is a violent reversal of airflow through the engine, accompanied by loud bangs and flames shooting from the exhaust. The FDR data appears to support this theory. The NTSB's investigative update states that after 17:13:11, the speed values for the low-speed rotor, N1, and high-speed rotor, N2, for the number. 2 engines showed minor perturbations. That's a technical way of saying the engine wasn't running smoothly. Something was affecting its operation. By contrast, Our engine 3 on the right wing increased and remained steady until about 3 seconds before the end of recorded data. The right engine was working fine, but one engine alone on a fully loaded MD-11 at takeoff weight isn't enough to climb. Here's the physics. Aircraft certification requires that a plane be able to continue a takeoff if an engine fails at V1, the decision speed. The aircraft must be able to clear the runway by 50 feet and continue climbing at a minimum gradient. This certification assumes loss of one engine, with the remaining engines at full power. It does not account for losing two engines simultaneously or near simultaneously. UPS 2976 was loaded for an 8.5-hour trans-Pacific flight. That means near maximum fuel load, near maximum cargo weight. The aircraft was at its heaviest and slowest point, with nearly all available power already deployed. When engine 1 separated, the crew would have seen immediate indications: fire warning, engine failure annunciations, asymmetric thrust alerts. First Officer Truitt at the controls would have applied corrective rudder to counteract the yaw from asymmetric thrust. If engine 2 then began compressor stalling, the situation transformed from survivable to catastrophic in seconds. Now they had only engine 3 producing reliable thrust mounted on the right wing. The asymmetric thrust would have been extreme, requiring massive rudder input to maintain directional control. The available power was nowhere near sufficient for climb. The crew had perhaps 10 to 15 seconds between rotation and impact. There is no checklist for losing two engines on takeoff. There is no simulator scenario that trains for this specific failure mode. Captain Wartenberg and First Officer Truitt were experienced professionals facing a situation no amount of training had prepared them for. Some analysts have speculated about alternative explanations. Could Engine 2 have been damaged by fire and smoke ingestion rather than solid debris? The wing was burning intensely and smoke could have affected the tail engine's performance. Could there have been a pre-existing issue with Engine 2 that the debris merely exacerbated? The NTSB's final report will need to determine whether the perturbations were caused by debris, fire, smoke, or some combination. And the NTSB's January 2026 update clarified that neither of the plane's two other engines were on fire before the crash. This suggests the flames seen from Engine 2 were not from an onboard fire, but from the compressor stall phenomenon itself, which produces dramatic flame events without necessarily indicating the engine is burning. What we can say with confidence: the FDR shows Engine 2 was not operating normally. The video shows Engine 2 producing flame patterns consistent with compressor stalls. The aircraft failed to climb despite having two theoretical engines available. The most likely explanation is that debris from Engine 1's separation compromised Engine 2's ability to produce normal thrust. This has implications beyond Flight 2976. The DC-10 family, including the MD-11, positions one engine in the tail directly behind the fuselage. This configuration makes that engine vulnerable to ingesting debris from either wing-mounted engine if those engines fail catastrophically. The certification standards for engine outperformance assume the remaining engines continue operating normally. They don't fully account for secondary damage that might result from the initial failure. American Airlines Flight 191 in 1979 also lost its left engine during takeoff. That DC-10 managed to climb to 300 feet before the cascading effects of the pylon separation caused a stall. The crucial difference: Flight 191's remaining engines weren't compromised by debris ingestion. The aircraft had power; it lost control due to leading-edge slat retraction caused by severed hydraulic lines. Flight 2976 appears to have had the opposite problem. The aircraft remained controllable, as evidenced by dashcam footage showing it flying level with zero bank angle just before impact. The pilots maintained control. They simply didn't have enough thrust to climb. Every accident is a chain of events. In this case, fatigue, cracks in the pylon, bearing assembly led to aft mount failure. Mount failure caused engine separation at the worst possible moment. Engine separation created a debris field that compromised the tail engine. Compromised tail engine left the aircraft with insufficient thrust for climb. Insufficient thrust meant impact was inevitable within seconds. For pilots, the lesson is sobering. Redundancy in aircraft design assumes failures are independent. Engine 1 failing should not affect Engine 2. But in practice, catastrophic failures can create secondary effects that compromise other systems. A debris field, a fire, smoke ingestion, any of these can turn a single engine failure into a multi-engine emergency with no recovery possible. The three pilots aboard Flight 2976 did everything they could. First Officer Truitt, at the controls, kept the wings level and the nose up, right until impact, Captain Wartenberg would have been managing the emergency, coordinating with Relief Officer Diamond. They flew the aircraft as trained, faced with a situation that training never envisioned. The NTSB's final report, expected in 12 to 18 months, will determine whether debris ingestion into Engine 2 was a contributing factor. They have the wreckage, they have the engine. They have metallurgical evidence that can show whether foreign object damage occurred to the compressor blades and turbine stages. Until that report is released, the debris theory remains the most compelling explanation for why a 3-engine aircraft couldn't climb after losing one engine. Something took out the tail engine too. Whether it was shrapnel, smoke, or fire, the crew of Flight 2976 never had a chance. 15 people died because a 3-inch bearing failed, and then everything that could go wrong did go wrong in the exact sequence that made survival impossible. When the final report is released, I'll be here to walk through it. Until then, we have data, we have video, and we have questions that only the wreckage can answer, right?